So in the other video that I just did on induction, I looked at two different types of induction. One where there was an inequality involving terms in terms of n, and there was another one that was a sum where you had up n terms. But there's a couple other types. One other type is if you have an induction problem involving divisibility. So for example, let's say that we're trying to prove that 5 to the 2n minus 2 to the 3n is divisible by 17. Okay, so is divisible by 17, and we're looking at n as an element of z plus. Okay, so let's start, same process. Let's look at our base case. So that would be 5 to the 2 minus 2 to the 3. That's 25 minus 8, and that's 17, which is 17 times 1. So we proved it for the base case. Let's assume 5 to the 2n minus 2 to the 3n is a multiple of 17 for some integer. And then let's consider the n plus 1th case. So plug in n plus 1, that becomes 2n plus 2. This becomes 3n plus 3. And now this one trips people up because there's no way I can just plug in my induction hypothesis in its entirety here. What I can do though is if I think about what my induction hypothesis is saying, it's saying 5 to the 2n is 17k plus 2 to the 3n. So let's try substituting that in. If I look at 5 to the 2n plus 2, I can write that as 5 squared, which is 25, times 5 to the 2n. I'm going to leave this other part, I'm going to break this other part up as 2 to the 3 times 2 to the 3n. Then I'm going to use my induction hypothesis. You've always got to use your induction hypothesis. This is going to go right there for 5 to the 2n. So I have 25 times 17k plus 2 to the 3n. Over here, I've got minus 8 times 2 to the 3n. Maybe you can see what's going to happen next. Distribute the 25, but I don't actually really care about what 25 times 17 is. I know that that's 17 times 25k. Then here I have 25 times 2 to the 3n minus 8 times 2 to the 3n. And that's the key part, is that again, I have 25 minus 8, leaving me with 17. So I have 17, and I have 25k minus 17 copies of 2 to the 3n. Well, guess what that is? That's 17 times m, and m is just a different letter. You don't need to use a different letter. Here you could have just said that this, you could have just grabbed this and written down that this is an integer, but I'm just going to write 17 times m, for m is some integer, and now the proof is done. So a lot of times in an induction proof, you have to do this slight manipulation right here, this box in blue. You need to change your induction hypothesis a little bit, because when you consider the n plus 1th case, there's no spot to throw the whole formula in. If you watch one of my videos where I do like a sum with the sigma notation, I can always just break the n plus 1 terms into the first n terms and then pop the induction hypothesis for the first n terms. And then all I have to do is usually like a common denominator. But with a divisibility proof, you gotta like change your induction hypothesis a little bit and then plug it in and things will pop out okay. All right, thank you for watching.